Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be covering Chapter 1.3, Solving Differential Equations by the Method of Separation of Variables. In Chapter 1.3, we will study a special class of first-order differential equations that can be written in the form y prime is a function of f of t times another function g of y, where the two functions are separate of each other. Such equations can be solved analytically by separation of variables and elementary integration techniques that you would have learned in Calculus 1 and Calculus 2. Depending on your calculus course, you may have even seen the method of separation of variables used to solve differential equations. To get started with this topic, let's look at some definitions. A separable differential equation is one that can be written in the form y prime is a function of t times another function of y. Constant solutions can be found by setting g of y equal to 0. The separation of variables method has 5 steps. Step 1. First set g of y equal to 0 to solve for any equilibrium solutions that may occur. Now, assume that g of y is not 0 and rewrite your equation in the form dy over gy is equal to f of t dt. And I think in this part here, I want to emphasize that I did skip a step. You probably want to think of this as first y prime could be written as dy over dt equals f of t times g of y. And when we write it in this form, what we're going to be doing is we're going to be dividing by g of t to get it in the denominator here, and then multiplying by d of t to get it on the right-hand side of the equation. We will then integrate each side to obtain an implicit one-parameter family of solutions, where the integration technique that you apply will depend on the specific functions that are given. After integrating, we will solve for y in terms of t to get an explicit solution, y of t, that we're looking for. If you have an initial value problem, you will then use the initial condition to solve for your arbitrary constant c. Let's look at a couple of examples of solving differential equations using this technique. Now let's consider the differential equation, the initial value problem. Y prime is equal to negative 2ty, where y of 0 must equal 3. Our first step in our process, again, is to find any equilibrium solutions. To look for equilibrium solutions, we want to think of this differential equation as a function of two different functions, g of y and f of t. So here, maybe you could think of y prime as negative 2t times y. And so explicitly written this way, this could be your function f of t. This is the function g of y that we are talking about. So to find any of your equilibrium solutions, we'll take g of y, which is just y, and ask when is this equal to 0? And we'll observe this is only equal to 0 when y is equal to 0. So this is our equilibrium solution. Step 2. Let's go solve for our differential equation. Let's solve the dE by separation of variables. And it's helpful to start by writing y prime as actually dy dt. And then you have your negative 2t times y. And when I separate my variables, I want to get all the y variables on the left and all the t variables on the right. So I will multiply to get the dt on the right, and then divide both sides by y to get it on the left. This will give us dy over y equals negative 2t dt. Okay. We now choose to integrate each side with respect to the variable that's there. So we'll integrate the left side with respect to y, and we'll integrate the right side with respect to t. Recognize that the antiderivative of dy over y is going to be the natural log of the absolute value of y plus some constant, since we have an indefinite integral. While the right-hand side would be negative t squared plus some arbitrary constant c. Notice that when I write this, we have two arbitrary constants, but we're using the same letter. Typically, we would actually represent these with maybe a C1 on the right and a C1 on the left and a C2 on the right. In actual practice, we don't keep track of these constants like I'm doing. I'm going to keep track of them for our first example so you can see how I will manipulate them. But in general, in my next examples, I will not keep track of the individual constants like I am doing now. Okay, let us now solve for y. To solve for y, you'd probably subtract the C1 from both sides. So we would have the natural log of the absolute value of y is just equal to negative t squared. And instead of writing C2 minus C1, I'm going to say plus C3, where C3 is really C2 minus C1. If C2 is some unknown constant and C1 is some unknown constant, then the difference of two unknown constants is still going to be some unknown constant, which I'm calling C3. Okay, let us continue to solve for y. To solve for y, we now got to get rid of the natural logarithm on the left-hand side. And so we will apply the exponential function e to both sides. And I want to emphasize that when you're raising the right-hand side to e, everything is the exponent here. Now, using the fact that this exponential function and logarithmic function are inverses, these will cancel on the left-hand side, and we just get absolute value of y equals e to the negative t squared plus C3. Here I want to use an algebraic property that we should remember that says whenever you have one exponent raised to one value times the same base, same exponent raised to another value, and this is a multiplication, that we write this as a sum of exponents. However, in this example, we want to be able to use this property in reverse order. That if you have an exponential or a base raised to the sum of two exponents, you can separate it as a product. Meaning that we can write ours as e to the negative t squared times e to the c3. To simplify this a little more, I'm going to write this as the absolute value of y equals, well, let's simplify this a lot right here. If c3 is an unknown constant, then e to the c3 is still an unknown constant. So let's replace this with a new constant. Let's call it c4. And so I can now write this as c4 e to the negative t squared, where c4 is really e to the c3. I now want to be able to argue why I can get rid of this absolute value sign. And my argument is very important that we do follow this. When we look at this argument for the absolute value of y, there are two cases that we should consider. First, if y is a positive number, then the absolute value of y doesn't change y. The absolute value of a positive number stays positive. So if y is a positive number, then we just have y equals c4 e to the negative t squared as a solution. Second possibility is if y is not positive, but y is less than 0. And remember what the absolute values do to a negative number. The absolute value of a negative number is always positive. I think we recall the absolute value of 3 is just 3. But the absolute value of negative 3 is also 3. And while that is true, I'd like to make an algebraic argument why this works. So here when we say the absolute value of negative 3, we know this has to be positive. So what we'll say is, well, if I put another negative in front, then the negative of a parenthesis negative 3 will still be 3. Of course, I only add this extra negative when we know our argument is negative. So here we're supposing that what if y is less than 0? We know it's negative. Then the absolute value of y can really be written as the negative of y is equal to c4 e to the negative t squared. Remember, in this case, we're assuming y is negative, so this means now the negative of a y value that's negative will now be positive, which accomplishes what this absolute value would do in the event that y is less than 0. Now, of course, I still want to solve this for y, so from here, let's divide both sides by negative 1. And simplify. This would give us y equals, well, I don't want to write c4 divided by negative 1. Let's actually just call this c5 e to the negative t squared, where c5 is really the negative of c4. Now, we considered two cases here. We considered what happened if y is positive, and we got this solution. We considered what happens if y is negative, and we get this solution. Notice they are of the same form. One has a constant C4, one has a constant C5, but remember these constants are arbitrary and unknown. So, in general, solutions are of the form y equals CE to the negative t squared. This represents your general solution to the differential equation. Now remember, though, we were given an initial value problem. We were asked to solve this problem where y of 0 was 3. So now let's solve the initial value problem. I'm running out of room on this page, so let me get this to fit in here. To solve the IVP, we want to evaluate our solution at 0. Of course, notice that y of 0 would be CE to the negative 0 squared, and we know this has to equal 3. This tells us C has to be 3. And so the solution to the IVP is going to be y equals 3e to the negative t squared. This is the solution to our IVP. Now, before I go into another problem, I want to tie this into with a problem that we were talking about yesterday. Yesterday, we were talking about direction fields. So let's look at this problem from another point of view from direction fields. And to help us with this, I'm going to go back to our differential equations Canvas course. Remember, on our Canvas homepage, under the quick links, I put a link for your D-field plotter. And in this problem, we're looking at, again, dy dt as negative 2ty. And notice it's giving me an error message. I think I recall now that I must put a multiplication symbol in between these terms. Okay, and now let's click on a couple of different places so you can see what solutions might look like. However, we're interested in what's going on at the point 0, 3 as an initial condition. Notice that this is our blue curve. We also found earlier our equilibrium solution going through 0, 0. So let's plot that one as well, which I'm not sure if you can see it real well, but it did show up in purple along the x-axis where y equals 0. Okay, I hope this is helpful. Let's try another example. Let's find the solution to this initial value problem. Again, let's not skip step 1. Let's find our equilibrium solutions. However, to find our equilibrium solutions, we probably have to rewrite our dE in a standard form. We have to get y prime by itself. So solving for y prime, maybe we can write this as y prime equals, let's move the t to the right-hand side, which would make it negative t, and then divide by y. Or maybe it'd be easier to write this as negative t times 1 over y. Again, I want to write these as a product of two functions. So in this product, this is the function g of t, or no, not g of t, f of t that we were talking about. And this is the function g of y. Now, when we're looking for our equilibrium solutions, we take our g of y, which is 1 over y, and recognize g of y is never equal to 0. This tells us that there are no equilibrium solutions. Now let's look for the rest of our solutions by the separation of variables technique. And again, my starting point with these problems is to always rewrite the differential equation. And I'm going to take our differential equation that we have written like this. And rewrite the y prime portion. So I want to write this as dy dt is negative t times 1 over y. And now we would like to get all the y's on one side and all the t's on the other. So to get y by itself, maybe we can multiply by y to get it on the right. Sorry, on the left. So this would be now y dy. Specifically, I'm multiplying this side by y and this side by y. And observing that now these y's will cancel, leaving the y on the left-hand side. Similarly, we'll multiply to get dt on the right. So this would be now negative t times dt. Now that we've separated our variables, we choose to integrate both sides. On the left, the antiderivative of y dy, again, the power rule would say this would be y squared, and then divide by 2 or multiply by 1/2. Now, technically, there's a constant right here. However, we don't typically write this constant. So I'm not sure why I'm writing it now. Maybe just for instruction. Let me continue, though. The right-hand side, the antiderivative of negative t would be negative 1/2 t squared. And again, this is an indefinite integral, so another constant. However, you'll recognize from our last problem that we did is we wanted to then solve for y, so we end up combining these two constants into a new constant, which I called C3. However, in this example, I'm not going to keep labeling these C1, C2, C3. I'm just going to recognize that when we look at C2 minus C1, this is just going to be some other constant that I'd like to call C. So I won't keep track of which C this is. I will not call it C3. I'm just going to refer to it as a constant. So now we'll have 1/2 y squared equals negative 1/2 t squared plus some constant. Okay, let's continue to solve for y. Maybe we could multiply both sides by 2. So that these 2's will cancel. And we'll get y squared. You'll probably want to distribute this 2 into the parentheses. So the 2 times the 1/2 t squared would be just negative t squared. And 2 times some constant. Well, since c is some unknown constant, 2 times some unknown constant is still an unknown constant. So here I'm just going to write c. But even though I'm writing just c, I want you to think of this as 2 times some constant is still just some constant. Okay, now we'll solve for y by taking the square root of both sides. Remember, when taking a square root, don't forget you need to have the plus or minus in front. And this will be our general solution. However, our problem was an initial value problem, so we should go further and solve for our value of c. Now for our IVP, recall we had y of 0 was 2. So let's find the specific constant that we need so that this will be 2 when you evaluate at 0. Evaluating our solution at 0, we get plus or minus. We're going to have to deal with this plus or minus in a moment. The square root of negative 0 squared plus c, and we want this to equal 2. Of course, 0 squared is 0. This ends up being plus or minus the square root of c has to equal 2. Considering what we have here, we actually only have one value. There's only one number that when you take the square root gives you 2. And we won't keep the plus or minus in front, because if it's minus, then we won't get negative 2. This tells us we really want just square root of c equals 2, which tells us c has to be 4. And we are going to be using only the positive root in front. This gives us the solution to our initial value problem as y equals, well, we said only going to keep the positive root of negative t squared plus 4. This is the solution to our IVP. I hope this is helping you. Let's look at another example. Find the solution to the, I said IVP, but this is not an IVP since I did not give you an initial condition. So let's scratch that part out. Let's just find the solution to this differential equation. Now, one of the first things I want you to notice is what kind of differential equation is this? And what I'm hoping you're recognizing is that this is a autonomous differential equation because the dE does not depend on the variable t. Notice that autonomous differential equations are always separable. Okay, let's get started. Let's not skip any of the steps we've been practicing. First thing to solving a separable differential equation is to look for your equilibrium solutions. So here, our equilibrium solutions are g of y that we're talking about is just y times y minus 1. There should be 2 equilibrium solutions. y equals 0, and y equals 1. This comes from the fact that we have two factors. The only way these are going to be equal to 0 is if the first factor is 0 or the second factor is 0, which leads to our two equilibrium solutions. Now let's solve the DE using the separation of variables technique. Again, I want to start by rewriting y prime as dy dt as y times 1 minus y. Separating variables, we'll multiply to get the dt on the right and divide by 1 y minus 1. Divide by y times y minus 1. Now don't multiply this. That's not going to help us. Here I want to write it as dy over y minus 1 equals dt. Following the process we've done on our last two examples, we're now going to want to integrate both sides of our DE. And what I'd like you to consider for a moment is what integration technique could we use on this left-hand side? And I'm asking you to think about things that you've seen back in calculus. I guess specifically, I'm asking you to remember the technique of partial fractions, or partial fraction decomposition. If you don't remember partial fraction decomposition as well as you might like, you might want to take a moment to just go and YouTube a couple of examples. I'm going to remind you how to do it in this one, but there are other cases that you might want to look at. With the partial fraction decomposition technique, our goal is to take the left-hand side, which is 1 over y minus 1, and write it as the sum of two fractions where the numerators, which are constants, are not yet known. So we want to find what does a and b have to be so that when you add these two fractions, it'll equal the same thing on the left. Now with this technique, what you'd like to remember is, or method, is that you want to get rid of your fractions. And you'll do this by multiplying both sides of your equation by your LCD. So let's multiply the right-hand side by y minus 1, and the left-hand side by y minus 1. Of course, when doing this, on the left-hand side, the y cancels, the y minus 1 cancels, and we're just left on the left-hand side with 1 equals. On the right-hand side, you'll distribute this product to each fraction. When the y minus 1 hits the first fraction, the y's will cancel, and we'll have just a times y minus 1. When this product y minus 1 hits your second fraction, the y minus 1's will cancel, leaving by. Now, there are different methods people used at this point to solve for a and b. I believe the easiest technique that I've seen is just to pick values for y that simplify this equation. For example, if we choose y to equal 1, if we choose y to equal 1, then 1 minus 1, or y minus 1, this ends up being 0. If y is 1, this turns into 0. So we end up getting 1 equals, if y is 1, this is 0, and 0 times a is 0. If y is 1, this just gives us b is 1, and we have our first constant. Okay, second choice. Let's not choose 1 this time. What if we choose y to equal, and I want to pick something that makes this term 0, so we pick 0. If y is 0, then we get 1 equals a. This would be 0 minus 1 plus b times 0. Of course, b times 0 is 0. This gives us 1 equals negative a, or a is really just negative 1. These are the two coefficients that we need for our partial fraction decomposition. Now, what these coefficients allow us to do is to rewrite this left-hand side integral. So now this is going to look like the integral of, remember the a, the negative 1 goes over the y term. So this will be negative 1 over y plus 1 over y minus 1 dy equals integral of dt. Okay, so we'll continue now. The integral of negative 1 over y is going to be negative natural log of the absolute value of y plus the natural log of the absolute value of y minus 1. Now, there would be an arbitrary constant on this left-hand side, but I'm not going to write it because I know in my very next step I'd be combining it with the arbitrary constant that came from the right side. So I'm going to skip that part and just say the antiderivative of the right-hand side is going to be t plus c, where this c would have been the constant that came from the left-hand side and the right-hand side combined together. Now, to make this be more familiar to us, I'm going to change the order of how I write this left-hand side. I want to write this as natural log of the absolute value of y minus 1 minus the natural log of the absolute value of y equals t plus c. And the only reason I'm doing this is because I want us to recognize how to simplify the left side. Written this way, we see it as the difference of two logarithms. Again, another rule from algebra I'd like you to remember is that when you see the difference of two logarithms, you can write this as the natural log of a quotient, y minus 1 over y equals t plus c. Now, it's common that some students don't remember how to solve this equation for y. So I'd like to walk you through it this time to remind you, but afterwards you'll remember the technique very well. If we're going to solve this equation for y, we will choose to exponentiate each side with base e. And remember, when I exponentiate the right-hand side, both of these become the exponent. Now I'm choosing base e because I know this e and the natural log are inverses, so these will cancel. leaving on the left-hand side just the absolute value of y minus 1 over y. And on the right-hand side, I'm going to use the property we talked about last time that says when you have a base raised to the sum of two exponents, you can write it as a product. Remember, going the other way, this would say when you multiply these two exponential expressions that have a common base, you add your exponents, which would be the same as we had earlier. And while this is correct, I would still like to write this one more way. I'd like to write it as y minus 1 over y equals c e to the t. Remember, if c is some unknown constant, e to the c is some unknown constant. Let's just call it c. One more step. In our previous example, we argued that this c could absorb the absolute values. Because if what's inside the absolute values is positive, if this is positive, the absolute values don't do anything. However, if all this is negative, we would divide both sides by a negative and the c would absorb that. Which allows me to say this is the same as y minus 1 over y equals c e to the t. Okay, let's continue to solve for y. To solve for y, I'm going to choose to multiply both sides of this equation by y so that these y's will cancel, which allows us to write this as y minus 1 equals yc e to the t. Now, we'd like to solve for y, so let's get all the y's on the same side of the equation. You could bring them to either side, but my choice is I'm going to bring this term to the left-hand side to get all the y's on the left, and then this minus 1 I'll bring to the right-hand side. This allows me to write this as y minus y c e to the t equals positive 1. We're almost done. On the left-hand side, we can factor out the common factor of y to write it as 1 minus c e to the t equals 1. And then we'll divide to get the y by itself and write our answer as 1 over 1 minus c e to the t. Now remember, this problem was not an initial value problem. So I'm going to stop here, and we'll say that this is our general solution. Now, this problem had a fair bit of integration techniques that you had to recall. In your homework, I know that they specifically remind you. They say something like, the partial fraction decomposition technique will be required on the following problems. So this will help remind you of this process. But again, if you're missing some of these skills or you need to review, remember YouTube has a lot of great examples. Let's look at one more example. This is the last one I have. Again, I notice here I said, find the solution to this initial value problem. But it's not an initial value problem. I didn't give you a constant. So we're just going to find the solution to this differential equation, the general solution. Again, here, I think it's going to be important for us to recognize that this is separable. It might not look like it with the y plus 2t as your exponent, but we can separate this with a little bit of algebra. So let's rewrite this. As y prime. Now remember, these exponents, when you have a base raised to the sum of in the top, you can rewrite this as the product of two exponentials. then we're using the rule that says when you have the product of two exponentials with a common base, you'd add your exponents. Now I want to regroup this, rewrite this as t e to the 2t times e to the y. And now written like this, you want to see that this is the f of t in our general formula we provided, times another function g of y, and so that this differential equation is separable. Now let's look for our equilibrium solutions. Remember, for our equilibrium solutions, we grab our g of y, which is, in this case, e to the y, and recognize that e to the y is never 0. This tells us that there are no equilibrium solutions. Okay, now let's solve the DE. So to solve our DE, again, we rewrite our left-hand side as dy dt equals t e to the 2t times e to the y. And we separate our variables, so let's again get all of our y's on the left-hand side. So we'll divide both sides by this e to the y term, and then multiply to get the dt on the right. So I'll write this as dy divided by e to the y equals t e to the 2t. And now we will choose to integrate each side of our equation with respect to y and t respectively. Now to help me with this, I still want to use some integration techniques we remember from calculus, and this division by e to the y seems unnecessary if we choose to introduce negative exponents. So maybe write this as e to the negative y dy equals the integral of t e to the 2t. There's not a negative there. dt. Looks like I forgot the dt on our previous line, so let's write that as well. Now, while technically the left-hand side is a application of a u substitution, I think because it's an exponential function, we would probably guess the antiderivative. In general, the antiderivative of e to the anything is e to the anything, so e to the negative y. But I'm pretty confident this is not right, because if you took the derivative of e to the y, it'd be e to the negative y times negative 1. And I don't have a negative 1. This prompts me to say that the antiderivative is negative e to the negative y. Again, technically I would have a constant here, but we're not going to write these constants. Now, the right-hand side, we want to recognize this integral. And I know I'm going to be asking you to remember a lot of things from calculus. Here, what I'd like you to remember is the integration by parts technique. And I know we have to use the integration by parts technique because the right-hand side is a product of two functions, and it's not a u substitution problem. If you were considering a u substitution problem, you'd probably be first considering maybe let u equal this exponent 2t, but then the derivative of 2t is 2, which does not show up down here, which tells me it's not a u substitution problem. So let's continue by the integration by parts technique. You'll want to remember from Calc 2, the integration by parts technique says that if you have an integral of the form u dv, that you could write this as uv minus the integral of v du. However, actually, when I remember doing Calculus 2, I didn't start here. The way I remember doing integration by parts is I start by determining what my u function is going to be, start by determining what my dv function is going to be. Then we differentiate to find du, and we integrate to find v. This is going to give us all the components we need for our formula. Now it's a choice that we make. What do we want to let u be? What do we want to let dv be in our original integral? So here I'm going to say let's let u equal t and dv be e to the 2t dt. I'm including the differential here because differential on the right has to be equal a differential on the left. Now if we differentiate this side, we get dt, or 1 dt. And if we integrate e to the 2t, and I think technically, again, this is a u substitution, but I can guess that the antiderivative looks like e to the 2t. Then if I were to take the derivative of e to the 2t, it would be e to the 2t times 2. And I don't have a 2 in my original problem, which prompts me to multiply by 1/2. Now the way I remember this integration by parts formula is by a triangle. It's going to be this u times this v minus the integral of this v times this du. What that tells us is that this integral t e to the 2t can be written as t over 2, this is the u times the v, times e to the 2t minus the integral, that's the minus, of this v times this du. 1/2 e to the 2t dt. In this problem, we took a complicated integral, t e to the 2t, and rewrote it in a simpler form with a simpler integral. Let's continue though. This is going to be negative e to the negative y, left-hand side. Right-hand side will be t over 2 e to the 2t minus, now the antiderivative e to the 2t is still going to be e to the 2t. But again, from our previous work, we know that the antiderivative e to the 2t is 1/2 e to the 2t. And there was already another 1/2 in front, so now 1/4. Plus our arbitrary constant. Let's continue to solve this for y. Maybe we could distribute this negative sign in the parentheses just to make it look a little simpler. And write this as negative e to the negative y equals t over 2 e to the 2t minus 1/4 e to the 2t. And then negative times c would be negative c. But if c is unknown constant, negative c is an unknown constant. And I still just write it plus c. Okay, let's continue to solve for y. Maybe divide everything by -1 on the left and on the right. So that we'll have e to the negative y is negative t over 2 e to the 2t plus 1/4 e to the 2t. And then c divided by -1, I still just want to call it c. Okay. Again, we want to get y by itself, so we choose to apply a natural log to both sides of the equation. Using the fact that the natural log and the e are inverses of each other, we will get negative y equals the natural log of negative t over 2 e to the 2t plus 1/4 e to the 2t plus c. And now we're just one step away. We wanted to solve for y. We still have a negative in front, so let's divide both sides by a -1 and write it as y is the negative of the natural log of the negative t over 2 e to the 2t 1/4 e to the 2t plus c. There was a good bit of algebra in this problem. But this does get us down to the general solution of this differential equation. Okay, this completes all the problems I wanted to work on with you from chapter 1.3. I think this should give you enough to get a good start on your homework. However, when we look at when we get together later on for our virtual class session, I'm going to bring up a couple more problems that we can look at, hopefully to help you with the algebra that we want to remember, and maybe even answer some questions that you want to talk about from your homework. I hope this is helpful, though, and I will see you next time.